Hello, YouTube. This is UMOS03. In the previous lesson, we learned about a searching algorithm. We learned about an algorithm called linear search. And basically what we did is we said if we wanted to look for a target element in a list or a tuple, basically what we could do is we could start at the beginning of the list or the tuple and check the first element. And if that's the target element that we're looking for, then we're done. But if it's not, we would have to keep going through and keep checking to see if, the elements at any of the index positions are the elements that we're looking for. And so what we did is we implemented and talked about that in the previous video. And the reason we're able to talk about searching for an element is because it's not hard to look at the index positions within a list or tuple, right? You could basically just increment by one each time. And that's what we did in the previous video. So we did it with the while loop, but it would have been probably even a little bit easier to do it with a for loop, right? So you could have said for counter in range of length of my people, for example. So that's what we did in one of the implementations, but we can go ahead and review the linear search algorithm, right? But before that, remember we were talking about sorting algorithms. So the whole goal is to build up this understanding of sorting algorithms, right? And in order to sort objects of a particular type, in order to sort person objects or point objects or computer objects or hot dog objects, right? Anything, any class that you want to create, you can actually sort them, and you can say that one instance of the class is less than another. And you do it with this magic method, this dunder, where you say underscore underscore LT underscore underscore of self comma other, and then you would just return the Boolean that you want to be true whenever someone says A less than B for two instances A and B of your class. So hopefully that makes sense to you, but that was the principle of sorting algorithms. And we talked about several of them, right? We talked about the bubble sort, which we said is the least efficient of the three, right? And we would basically have a very simple implementation for it. But this is a very clean method that has doc strings, right? And it accepts an input and it tells you what it returns. So it returns a sorted version of the list, right? And the same thing for insertion sort and the same thing for selection sort. So these are three sorting algorithms that we talked about. Now to the three, insertion sort is the most efficient of the three, and selection sort is in the middle, and bubble sort is the least efficient of the three. But we talked about the implementations for those, right? And then we also talked about this person class with the name instance variable and the age instance variable, and also the properties and the setter methods, which allow you to return or modify the value of a strongly or weakly private instance variable. So hopefully that's clear to you. But then we also have these other magic methods and also the get item and set item dunders, which allow you to return or modify values within a dictionary, right? As though an instance of a class were a dictionary where you could basically feed in a key and either return a value or, modify the value associated with that key. That's the get item and the set item dunders. So hopefully that's clear to you. In the linear search algorithm, basically we accept two inputs. So we accept a list or tuple that we're searching through, and then obviously a target element that we're trying to find. And we're going to return the index position of the first occurrence of the target value, or -1 if it did not appear in the tuple. So there's no reason for this to throw an exception, right? It's obviously either just going to return -1, or if it's in the list, it'll return 0 or 1 or 2 or 3 or wherever it's at. But it's going to be the first occurrence. And then basically once we mark it as true, it's going to stop going through the loop. So even if you have 4, 4, 4, 4, 4, and you're searching for the number 4, it's going to say index position 0 because the first 4 occurred at index position 0. So hopefully that's clear to you. So we say result equals -1. This would happen by default. And then a counter equals 0 to basically keep track of where we're at in the list or tuple. And we would say found equals false, right? By default, we obviously haven't found the element yet. While counter is less than length of my tuple and not found, if my tuple of counter is equal to target, result equals counter, and found equals true, right? So we would just want to update the result with whatever the current index position is and update found to true, right? And then this Boolean would no longer be true, right? Because not found would no longer be true. So we would be done. And so we would just go ahead and return the result. But every time we do go through the while loop, we would have to remember to increment counter by 1. But you'd want to return the result to that. And we saw examples in the previous video, right? So I don't know exactly what's getting printed on the console right now. We already have 0 and 5, right? So I think that was just a couple of examples I was doing right here. But yeah, so we have it right here. So remember, if we say linear search of some tuple with 11, right, it returns 0 because that's the first time that it occurs, right? What if you had said 11 plus 4 and 11 plus 12, and then you said here, it said 11 plus 10, right? Well, now there's no more 11s in the tuple, so now you get -1, right? And then, so hopefully that's clear to you. And then we also talked about how you could do this with person objects, right? So what if you wanted to search for a particular person, but instead of passing in a person object, you know, for your list of person objects, you want to just pass in a string and you want to look for someone by their name. So what you would do is you would say result equals -1, right? It's still by default. We haven't found them yet. And so we would just say, oh, they're at index position -1. And you would say for counter in range of length of my people, current guy equals my people of counter. Okay, so current guy is referring to an instance of the person class. But then when you say current guy of name, remember with the get item dunder that we wrote, we say that current guy of name, if we go ahead and look back up at that, it says that we're supposed to return the value of the name instance variable. So it would return the name instance variable. So it would look at that, you know, the current name that it's at, that string, and it would compare it with the string that we passed in. And if they're equal, then we would be done. So we would say result equals counter and then break out of the loop. So this is an alternative. Either you keep up with whether or not it's found, or you just break out when it is, right? And then you would just return the result. So that's another implementation. And we saw that in the previous video. That's why we got 5 when we ran this in the previous video, but we were pretty rushed at the end. But what we said is we said tuple people equals UVWXYZ. And so what if we said linear person of tuple people with Angela? Well, remember, if we go ahead and go back up, we defined Z as a person of Angela with 40, right? So the first time basically that Angela shows up in the names column, essentially, in this first parameter is at index position 5, because we were looking at the get name at the name instance variable each time. So hopefully that's clear to you. In this lesson, we want to talk about a new type of searching algorithm, okay? And so with the linear search, it's pretty inefficient if you have a sorted list. So what if you had something sorted like a dictionary, right? Where you didn't know the definition of the word textbook. You had no idea what that meant, okay? And so what you could do is you could either pass through the dictionary one word at a time, and you could look at, you know, Arthur, aardvark, apple, afterwards, aftermath. I don't know if those were sorted exactly, but you'd have to look through all the A's, right? And then all the B's and then all the C's. And it turns out there's actually a lot of words in the English language, if you didn't know that already. So it would actually take you a long time to find the word textbook, okay? And so if you wanted to know the definition of the word textbook, a better strategy would be to start maybe around the middle of the dictionary, right? Or closer to the end. But you would basically divide the dictionary in 2 each time. And you would say, basically, I'm going to split the dictionary in half. And if the starting letter, if the T that I'm looking for occurs after the letter that I flipped to, well, then I know that my word is going to be in the second half of the dictionary. But if the letter T that I'm looking for, right, or if I were looking for F or B, if that was in the first half of the dictionary, then I could eliminate the second half of the dictionary. And that's an algorithm called binary search. And basically, if you have a sorted list or a sorted tuple, then it's much faster to use binary search in order to look for an element or to find the index position of a target element within your list or tuple. So what we're going to do is we're going to study the binary search algorithm. So remember, we were talking with linear search about starting at the beginning, but if you have a sorted list, if you have a list that's sorted or a tuple that's sorted, then it will be much faster to use the binary search algorithm, okay? And apparently it's also called logarithmic search, but I've yet to hear it be called that. But it's a search algorithm that finds the position of a target value within a sorted array, okay? So we already see a difference between binary search and linear search, is that binary search requires a sorted array. Well, if it requires a sorted array, then why would you want to use it instead of linear search, which doesn't, okay? And when they say array here, that just means list or tuple, okay? But what we're going to do is it compares the target value to the middle value of the array. So what you would do is you would think about a dictionary, you would think about a sorted list, and you're just going to immediately look at the mid value. And if they're not equal, then the half in which the target cannot lie is eliminated, and the search continues on the remaining half. Again, taking the middle element to compare the target values. So you're going to compute a new element each time, right? Because your left and right endpoints are changing along the way, okay? And it runs in logarithmic time. And that means that it's a lot faster than linear search, except for in small arrays, right? So if you only had 5 elements, 1, 2, 3, 4, 5, and you were looking for the 1, then, you know, you'd want to start near the beginning, right? But if you were looking But if you were talking about a lot of elements, right? If you were talking about, you know, sorted ID numbers or something like that, you sorted it according to, you know, selection sort or insertion sort, and then you had a sorted, you know, list, then binary search would be a lot better. This is a much more efficient algorithm, just like we said that insertion sort was more efficient than bubble sort. So hopefully that's clear to you. But what we're going to do is we're going to look at the code for it. We already talked about the code for linear search. So how does binary search work? So what we're going to do is we're going to pass in two required inputs, right? And we've talked about default arguments. We talked about in lessons 43 and 44 and 45 about default arguments. And we said that, you know, with these left and right that you pass in here, you can either specify values for them, but you don't have to. And if you don't, then left would just take the value 0, it's an integer, and right would just take the value initial, that's a string. But it says binary search implementation, so it's an iterative method which uses a while loop to compute a middle element between two changing left and right endpoints of a sorted sublist, with the target element being identified when the middle element equals the target element. So we're going to be comparing the middle element to the target element every time, as the Wikipedia article said. But we have to accept at least two inputs, right? And you can optionally accept the left and right, but don't actually worry about that, because we're actually just going to run it with these two inputs. But you need to at least pass in a list or tuple in which to find a target element and a target, so a target element to search for, okay? And then left is going to be defaulted to 0 at the beginning, and right is going to be defaulted to the word initial. And then what we're going to do is we're going to say if right is equal to initial, then right equals length of sorted tuple minus 1. So just readjust right to length of sorted tuple minus 1, basically if it was not brought into the function, right? Basically, if it took this default value, then we're going to assign it to the length of the sorted tuple that we passed in minus 1. So it would be basically looking at the last valid index position, right? If the length of a sorted tuple is 26, then the last valid index position is 25. So hopefully that's clear. And how it works is we're going to say result equals -1. Okay, so now basically left, what we would do is we would say left is the first valid index position, so that's 0, right? And then right is the last valid index position, so that would be the length minus 1. Okay, so because the first comparison that we look at is the entire sorted list, right? The first time you look for the word textbook or the definition of the word fart, you would want to start from A to Z. You would want to look at the entire dictionary, right? The first word to the last word. So what you're going to do is you're going to say result equals -1. By default, we haven't found it yet. And remember, you need a sorted list or tuple. It doesn't work with an unsorted list or tuple. If you have an unsorted list, you need to go ahead and apply bubble sort or insertion sort or selection sort. And we have 3 or 4 videos that talk about how to do that. But you're going to say result equals 1. Okay, by default, we have not found the target element. And what we're going to do is we're going to say while left is less than or equal to right. Okay, so while left is less than or equal to right, these are 2 variables that we're keeping track of, okay? And most cracks, most calls to this binary search algorithm, right? We're just going to run it with these 2 inputs. We're just going to run it with a sorted tuple and a target element to search for within the sorted tuple, okay? So just worry about, but left is going to be basically 0 that we assigned it to by default. And then right is now going to be length of sorted tuple minus 1, okay, as a result of this if statement. So we say, while left is less than or equal to right, mid equals the integer division of left plus right over 2, right? So then basically, for example, if left equals 0 and right equals 9, then mid is going to be equal to 4. So it's basically going to look at the midpoint element within the list, okay? And you can't look at an element at a half index position, right? So we couldn't say list of 4.5 or tuple of 4.5. That wouldn't make any sense because index positions have to be integers. So that's why it says over 2, okay? And then we would just want to basically make sure that, you can kind of actually remove this, but I was just saying we would want to make sure that the mid value is equal to the integer form of the mid value, right? Like presumably this would have to return an integer, otherwise something wouldn't be getting computed correctly. But I didn't get any runtime errors with this. But anyway, that's a review of an assert statement, right? If you assert a particular Boolean, then the code keeps running if the Boolean was true, and then it throws a runtime exception. It throws an assertion error if it's not, and then you could go ahead and catch an assertion error if you wanted to. But anyway, if sorted tuple of mid is less than target, so basically, if the middle element is less than, and we talked about sortable elements, right? So we could talk about one person being less than another person on account of the first person's name being shorter than the other person's name. We talked about that in previous videos. But if the middle element, right, if you just crack it open, the middle of the dictionary, you look at M, for example, right? But your target element is T. You don't know the definition of the word textbook. So if the middle element is less than the target value, then what you would do is you would reassign the left element to the mid plus one. So this actually chops off the left half of the sorted sublist. So what you would do is only look now at the right half. Okay, so what this would do is it would reassign the left endpoint. So now instead of looking from A to Z, you would basically be looking from M to Z, right? You would only care about now half of the elements in the dictionary. And you can think about how dividing by 2 each time would be a little bit faster than subtracting one word each time, right? This binary search is intended to be a hell of a lot faster as long as you have a sorted list or a sorted tuple. But you would say if the middle element is less than the target, readjust the left endpoint. Otherwise, if the middle element is bigger than the target, you would want to readjust the right endpoint. And then now you would, chop off the mid. So now you would chop off the right half. So now you would reassign the right endpoint to be just to the left of the middle, because only the first half matters, right? Only the first half of the dictionary matters if the middle element was already too large, right? If your target element was less than the mid element, right? But if the mid element is equal to the target, well, this is success, right? This is success. This means that you're done. And so you would update the resultant index position to whatever mid is, right? Mid corresponds to the index position, right? And then you would break out of the loop. Then you're done and you would stop doing these comparisons. But this is not a recursive algorithm. It would just, this while loop would run over and over again. But you only call the function once. And the only two things that you need to pass into it are sorted tuple and target. You don't really need to worry about passing in values for left and right. But if you really want to, you could pass in 0 and length of tuple -1. It would have the same effect. But anyway, you just pass in those first two inputs and you would just return the result. So we just want the index position where it occurred. So what we can do is we can basically just return the resultant index position of that target element that we were looking for within the sorted list or tuple. And I have a little example here so we can think about applying binary search for a list of sorted elements, right? So obviously this would work for integers and floats, right? But it would also work for sortable elements in general. So if we think about instances of our person class that we created, remember we created a person class that we've been talking about for multiple videos. And one of the things it does is it has a constructor that assigns the values of the name and age instance variables. So what we do is we do that 7 times and we add those 7 elements to a list. And then just in case that list is not sorted already according to the length of the name instance variable, which is how we decided to compare 2 instances of our class when we wrote our less than magic method, we can go ahead and sort the list, right? So we can sort the list according to that definition. So we would say my guys equals insertion sort of my guys. So we would use one of these sorting algorithms that we talked about to get the list into sorted form according to the length of these people's names, okay? And then what you would do is you would say for R and my guys, print of R, okay? And so what does this do? This uses the str method that we wrote, right? We said that the str dunder, the str function specifies the string representation of an instance of a class. And so we have that method defined right here that we return their name and then is, and then the string representation of their age and then years old. So hopefully that's clear to you. And then we could basically say the index position of Chris, and we could find Chris within this list, because what we would realize is that basically, I guess, or what we could do, instead of hard coding Chris in here, we could basically say, Y of name. So we could use the get item dunder that we've been talking about, but we could basically be looking for Chris in here, and then we would do a binary search. And here in our binary search algorithm, we actually accepted the target, right? We actually accepted the element that we were looking for. So we would say index position, then Y of name if we were looking for Chris, and then string of binary search of my guys and Y, because we said that their 2 required inputs are a sorted list and a target element. So now if you go ahead and run it, you get the sorted names according to the length of the name. So you get sorted person objects in the list. and you get that the index position of Chris was 3, and we didn't write it exactly beautifully, but that's the idea. So hopefully that's clear to you, and we'll review in the next video. For Mimosa 3, thanks for watching, and please subscribe.